Assalamualaikum warahmatullahi wabarakatuh, and have a good day everyone. Okay, this is the topic of my presentation today, development of ArcSWAT surface runoff model for estimating urban precipitation recharge. And before I proceed, I would like to introduce myself. I'm Rohazaini Muhammad Jamil from University Malaysia Kelantan. Okay, for the introduction, as everyone knows that one of the essential parts in groundwater resource management is estimating groundwater recharge, and it may be need to be estimated partially and temporarily. More than 50% of world's population now live in cities. As urban water demand is huge, many cities are struggling to get enough water. Recharge is a critical determining factor for management of urban water supplies for cities overlying aquifers. And recharge is usually changeable in time in response to climate, land use, and subsurface infrastructure. However, estimating recharge in urban environment is more complex than rural environments, as there are many sources and pathways for recharge. Buildings, roads, land cover permeability such as paved and unpaved, and other surface infrastructure combined with man-made drainage networks to influence recharge. No generally accepted method is available for estimating urban recharge, since partial heterogeneity is a significant feature of urban areas. A GIS approach is attractive to be applied. Thus, this study is trying out an existing GIS-based system, which is called ArcSWAT, that has been used mainly on non-urban areas to estimate urban recharge. The objective for this study is to develop an ArcSWAT surface runoff model to estimate urban direct recharge and compare the output with the results from other recharge models of the same area. Secondly, we are going to discuss about materials and approach that have been done in this study. The ArcSWAT ArcGIS extension is a graphical user interface for the SWOT model. The ArcSWAT ArcGIS extension requires data on land use, soils, weather, water use, management, surface water, and stream water. This extension can be used to simulate a single watershed or a system of multiple hydrologically connected watersheds. Each watershed is first divided into subbasins and then into hydrologic response units, HRUs, based on the land use, slope, and soil distributions. This figure shows SWOT water routing. SWOT model uses water balance to simulate water routing through the system. Study area. The unconfined part of the Triassic sandstone aquifer in Birmingham, United Kingdom has been chosen to trial ArcSWAT due to data availability. Birmingham broadly represents many long-established industrialized cities in Europe. The sandstones is covered by thin quaternary deposits comprising clays, sands, and peat. The sandstones dips to the southeast from 0 meter thickness as its western feather range to about 150 meter at the Birmingham Fort. The time period for this study is from 1990 to 1999. For the research approach, this study uses the runoff estimation code in ArcSWAT in ArcGIS version 10.2 as a tool to estimate recharge. Data used included digital terrain model, soil type distribution, land cover distribution, and daily rainfall as well as potential evapotranspiration PET data. From land use, soil, and topographic distributions, SWOT defined 367 HRUs and linked these into the 59 subbasins. Recharge mechanism in SWOT model. The principal aim of SWOT is in calculating the water balance. Meanwhile, recharge is one of the components. The recharge on a given day is calculated using this equation, where recharge I is the amount of recharge entering the aquifers on the day I. Groundwater is the delay time or drainage time of the overlying geological units in days. WCEP is the total amount of water that exceeds the bottom of the soil profile on day I. And W recharge is the amount of recharge that enters the aquifer on day 1. Very briefly, surface runoff is calculated within SWOT at daily time steps by a modified Soil Conservation Service curve number method or the green-armed infiltration method. The curve number, which is a measure of the amount of runoff, is modified in SWOT depending on antecedent soil moisture content as well as land cover. This is the equation for SCF's curve number, where QSURF is the collected runoff or rainfall excess, R day is the rainfall depth for the day, IA is the initial abstraction, which includes surface storage, interception and infiltration prior to runoff, and S is the retention parameter. Next, we will be discussing the results. The predicted SWOT model recharge to the study area was compared with the results from 3 previous modeling studies, UGIF, 4RH, and 4RAH. This table represents the root mean square of error RMSE among the recharge models that are presented. A low value of RMSE indicates a better fitting model. The results show that 4RH with mains leakage factor has the lowest RMSE than other models. Meanwhile, UGIF and 4REH without mains leakage factor give RMSE value of 38.89 and 28.08 respectively. These 3 figures plot the correlation of recharge for each models against the SWOT model. The results show that SWOT model has a strong positive relationship between 4RH and 4REH. However, UGIF gives a moderate positive relationship with SWOT model. For the discussion and conclusions, urban area recharge, that including mains leakage SWOT model, has been estimated using ArcSWAT ArcGIS extension, indicating that a surface water runoff model can be utilized to estimate recharge in an urban setting. The results are broadly similar to the total recharge predicted by previous models of the area, but with significant differences in some cases, such as mains leakage factor. Detailed information on groundwater recharge in space and time provide basic data for management of urban aquifers can be utilized in ArcSWAT. However, one of the questions in this case remains: is the differences between the recharge estimates significant in terms of groundwater resources? Therefore, a future additional research would be suggested in order to understand the remaining case. Before I end this presentation, I would like to thank the Ministry of Higher Education of Malaysia, UMK, for the funding. the British Geological Survey, Ordnance Survey, Meteorological Office of UK, and also I would like to express my gratitude to Professor John H. Telem from University of Birmingham for his assistance, helpful and critical comments while preparing this manuscript as well as in this study. These are the references that I use in this study, and thank you.